let P, Q and R be statements. Quotes में मंदार नहीं statements. Then P and Q are P and Q O. You know that this is ending.
Yeah.
I will use that. Make O. P and Q R is logically equivalent to P and Q, O, P and R. Right? Let's prove this thing. How do we prove? Prove. Let me write. P, O, Q and R is logically equivalent to P, O, Q and O. P and Q, O, Q. Right? I'll make a proof and prove. Say suppose we want to prove the first one, Roman 1. So how do you think? How should we proceed?
First we have to suppose that the first one is true and prove that one, and this one is true and prove that one.
Okay, let me write. Suppose P and Q, O, R is true. Then what can I say?
Therefore, P is true and QOR is true.
Thus, P is, I will not write course, you don't know. I will design. Suppose this one is true, then thus P both P and QOR. This is English and are true. Then what can I write?
Then P and Q is true, or P and R is true.
No. That's why you are finding it difficult to write proofs. That is the reason I am doing this thing. I have both these are true and so both, then thus both P and QOR are true. How have I written here? Oh, yeah. P and QOR are true. I am asking, we are on the way to prove this side. So what shall I write? What you said is?
The thing we need to show.
Eh?
The thing we need to show.
Yeah, thing to be shown.
Since QOR is true,
Okay. QOR is true, comma,
Q is true, O, R is true.
Q is true, O, R is true.
Case 1 to
Okay, case 1.
this one. Assume that Q is true.
Assume that Q is true.
Then
Then
P and Q is true.
then P and Q is
True.
true.
Case 2.
No, I haven't proved that. No.
Oh, therefore P and
Therefore,
P and Q O which one? R is true. P and R is true.
okay, so this one assume Q is true, then P and Q is true, since over here we have said both P and Q O R are true, no? Okay, so we have shown that P and Q O, P and R is true. Now case 2, we need to be able to write very little things. So in the proofs, what you get is not little, but this background helps a lot. Okay, now what is case 2?
Now assume
Now assume
that R is true.
assume that R is true.
Then P and R is true.
Then P and R is true. Okay,
Hence
hence
P and R in brackets.
P and R is true, no? I have it there.
Yeah, P and R in brackets or P and Q in brackets is true.
It's fine.
Yeah.
Without changing the order. P and Q, O, P and R is true. Okay.
From case 1 and 2
Cases
cases,
1 and 2.
P and Q or P and R is true.
P and Q, O, P and R is true. So, P and Q, R is true. I have shown that this is true. Okay, now what? Now, as you are saying, we have to assume this side. So let's assume. Okay, proof. I have written here soup because I have increased soup. Suppose. Okay, now suppose what?
Now suppose P and Q or P and R is true.
E and Q, O, P and R is true.
Therefore,
Therefore,
P and Q is true. Or
we want to say this one is true or that one is true.
yeah,
So we can say then, therefore, at least one of P and Q P and R is true. At least one of them is true. Okay, then
Case 1.
case one.
Assume that P and Q is true.
P and Q is true. Okay.
Hence,
Hence,
both P and Q are true.
both P and Q are true. Okay.
Hence, P and Q, OR is true. That statement is true. Okay.
You are jumping, that is why you find it difficult to learn. Hence, both P and Q are true.
Therefore, Q OR is true.
You cannot jump. Q O R is true.
Now we can say that one.
What can I say? Hence,
Hence, P and QOR is true.
okay, so we have proved in case one, now case two. You jump a lot. That is why you do mistakes. Case two. I mean, that's why I'm doing this to today. Case two.
Now assume that
Now assume that
P and R is true.
P and R is true. True.
Hence, both P and R are true.
Both P and R are true.
Thus,
Thus,
R Q and QOR is true. Therefore, P and QOR is true.
hence in either case, P and Q are true. Right? Then අපි ඔප්පු කරලා තියෙනවා. If this is true, then this is true. If this is true, then this is true. So now can I say that it's logically equivalent? Because if you are going to put all the cases, they may be having false situations. So we are not going to worry about it as it is also. Thus, P and Q are is logically equivalent to P and Q or P and R. I'm terribly sure now we have proved it. You know, you have to, when you write a statement, you have to take the responsibility that it is correct. Even if I say it is wrong, no sirs, I'm right. You have to have that nature. But in your case, what happens is you jump right away. That cannot be done. Let's do anyway quickly. These are all distributive laws, by the way. Why? Because you are distributing P to both Q and R. You are distributing P to both Q and R. As a result, these are all distributive laws. Okay, so back to 2. Now, what do I say?
Suppose that
Suppose
P O Q and R is true.
P, O, Q and R is true. Okay.
Therefore, P is true. Q and R is true.
Therefore, let's say it's good to practice this language. At least one of P, comma, Q and R is true. What you are saying is correct. But it's better to write this way because O comes with this for some, there exists so at least one. They go together. Okay. Therefore, at least one of P, comma, P and Q are P. I write comma because to save writing. Okay, now what?
Case 1.
Case 1.
Assume that P is true.
Assume that P is true. Okay.
Then P O Q is true.
Therefore, P, O, Q is
True.
true.
And can we combine this?
And what?
And P O R is true.
So good to write therefore both. Because you have to get to the analysis language. What you said is correct. I didn't say it. So therefore both
For both P O Q is true. Therefore both P O Q, comma P O R are true.
are true. Thus,
Thus, P O Q and P O R is true.
okay, so in case 1 we have proved it. P, O, Q and P, O, R. Now case 2.
Case 2. Now assume that P and R is true.
So therefore at least one of P, Q and R no, we have.
Is Q and R is true.
Then assume Q and R is true. Okay?
Therefore both Q comma R are true.
Okay.
Hence Q let's say P O Q is true. Combine those. Hence both P O Q or P O Q, comma P O R is true. Are true.
Thus,
P O Q and P O R is true.
so in this case we proved it, P, O, Q and P, O, R, hence in either case. P, O, Q and P, O, R is true. okay, I want to go to restroom and come. Because page 53, that is very important. Not P and Q is not P or not Q, right? Not P or Q, not P or Q is not P and not Q. Let's prove that also. Certain things we are not going to prove, certain things we will. You have seen from the book that there are something called truth tables. So, truth tables is correct, but the disadvantage is that without feelings, by a table you decide. So that's why I think in English these are called De Morgan's laws. Must be some German guy, I don't know. De Morgan's laws, still in place. Let P give B statements. Then not this book, I am using this symbol for not, you have seen that, no? Not P and Q is logically equivalent to. You know this thing, but I want to make sure you can say it in English. Because we are learning in English now. It's logically equivalent to not P or not Q. And to not P or Q is logically equivalent to not P and not Q. Let's see. Quickly, let's go. Proof. 1. Let's prove this. Okay. Not P and Q is logically equivalent to not P or not Q. You have seen this for not, no? So, how do I start? How about you?
Suppose not P and Q is true.
Suppose not P and Q is true. Then what do we know? Not P and Q is true. What do we know then? Next thing, not away. You kind of
My mind goes to straight to that.
not P and Q is true. Then what do you know? Immediate thing. Not P and Q is true. Suppose there is a man here. This guy is a liar. This guy never tells the truth. He always lies. Suppose he says something is true. What do you know about?
It is false.
What is false?
The statement he said.
So, suppose not P and Q is true, then
Uh, then P and Q is false.
P and Q is false. Ah, you took long.
Sir, isn't that the same thing?
Eh?
Isn't that the same thing?
Yes.
I mean, we don't have to say that.
Then you can say, you don't have to say this also. Then P and Q is
False.
false. You know now, P and Q is false. So then what can you say?
Then P is false. OQ is false.
P is false, OQ is false. Yes?
Yes.
Are you sure? P is false, OQ is false.
One of them has to be false.
Then P, again you are saying at least one of, is that?
Yes.
P is false. Then
Then can we straight go to the input? Not P or not Q.
Separate between two cases.
then at least one of P, Q is false.
Case 1,
Without taking case one,
assume that P is false.
then cannot you say this way then at least one of not P, comma not Q is true?
Yeah.
Because at least one of them is false. Then if you take the negation, then at least one of them is true. Can you see from here you are saying you told me it is the same thing, but from here you cannot come here. You have to write this line. You ask me, isn't that the same thing? Of course they are the same thing. Thus, not P, at least one of them is true, then not P or not Q is true. Right? Not P or not Q is true. So, if I assume this is true, I get the right hand side is true. Conversely, what do I write?
Now suppose not P or not Q
Is
is true.
true. Then
Then not P is true or not Q is true.
gain at least one of both.
At least one.
Not P, comma not Q is
Is true.
true.
Hence,
Means
at least one of P or P comma Q is false.
therefore
Therefore, P P and Q is false.
so
So, not P and Q is true.
true. Not bad, but Let's see, anyway, this is still, yeah, the garden. Kindergarten. Now, so, I mean, we have proved if this is true, then this is true, if this is true, then this is true. Thus, not P and Q is logically equivalent to not P or not Q. Okay, now we have done that. So let's go to 2. So what do I write?
Suppose not P or Q is true.
Not P or Q is true. Okay?
Hence,
Thus,
P or Q is false.
is false. Hence,
Hence, both P, Q are false.
hence,
Hence, P and Q is false.
is that right?
That's it.
No.
You need to keep in mind what needs to be proved. That's important. Whenever you are so we are coming to not this, no. At the end of the day, even today still will be coming to certain not difficult but little higher things. So here we have assumed this, we want to prove this. So we should try to say something related to this. Both PQ are false.
Then P is false. Not P, not Q are true.
Thus,
Thus, not P and Q is true.
okay. Now, conversely, suppose that what?
Not P and not Q is true.
Thus,
Thus, both not P, not Q
both not P and not Q
are true.
are true. Hence,
Hence, both P, Q are false.
they are true here, no? Sometimes I can are false. Hence, therefore,
Therefore, P or Q
is
false.
hence,
Hence, not P or Q is true.
so we assume this thing, prove this thing, we assume this thing, prove this thing. So that's not P or Q is logically equivalent to. No P and no Q. So this is a very important one. That's why I chose this to be done on the board. Then I am saying 10 to 10.2.1 theorem. Is that an important theorem? Because we need to finish this since I did not really. What is this 10.2.1 theorem? Let P and Q be statements, then the statement P implies Q is logically equivalent to not P or Q. That is a very important result, whether you prove it or not. Whether this all the quantifiers can be written using implication. All of them. P implies Q, of course, or there is no name. P and Q, P or Q, P if and only if Q. Everything can be written using implication. So that way it is important, and on the other hand, somebody can wonder, this says P implies Q. What it means to us is if P is true, then Q is true. However, it is logically equivalent to this one says not P or Q. Right away doesn't look true, no? At once, but it is. So, because it is important, we are using this sort of things in our analysis proofs a lot. I have written let P and Q be statements theorem. Let P, Q be statements. Then the statement implies Q is logically equivalent. Not P or Q. Without a proof, do you feel it is equivalent? Then do you feel? If you feel that they are the same, that's very good. But with the time, you may agree. I mean, if we talk, Putta, you said you can't believe, sort of. So how can you convince us that they mean the same thing?
So, in order for P implies Q to be true, either P is false or P is true and Q is true. If P is false, not P is true, thus not P or Q is true. If P is true and Q is true, not because Q is true, not P and Q is true. Thus, when P implies Q is true, not P or Q is true. And if P implies Q is false, P must be true and Q must be false. Since P is true, not P is false. Thus, not P and Q is false.
Yes.
If we take the negation of both statements, we can show that it's equivalent.
Okay, but he is saying if you take the negation of both sides, we get the same thing. That is one way of doing it. But what my question is something different. Somebody says, if it rains, ground gets wet. And somebody else says, A said, if it rains, ground gets wet. Somebody else said, no. If it doesn't rain, no, if it doesn't rain, oh, ground is wet. So they mean the same thing. My question was, do you feel that they see? Not the proof I am asking. No, in maths, your feelings are very important because when you are going to prove results, now he is going to do PhD in analysis. So, sometimes you, by the way, that is something you need to understand also. Sometimes you get a PhD because you spent 2-3 years, you could not prove, but you sometimes prove Pythagoras theorem, right? Because since you have spent time, your advisor will ask you to do something because he knows that you have still time. So you are getting a PhD actually without doing anything. But sometimes you get PhD because you have done something really concrete. So having a PhD does not imply that the person has done something that nobody else has done. Actual PhD is you have done something that nobody else has done. That's why I am asking here, somebody says, if it rains, ground gets wet. And somebody else say, no, it doesn't rain. Oh, ground is wet. Do you feel that it is the same? If somebody says in English.
I mean, for the ground example, I can understand it is true. But when it comes to
Yes. No, if you cannot, I cannot say it is good or bad, but if you feel that way, that is very good. That's my point. If you feel that way, because many students don't feel it. Here, what it says is that if P is true, then Q is true. Over there, what it says is P is also Q is true. However, by definition, if you go to the definition, of course you know it. But if P implies Q, if P is true, Q is true, no? If P is true and Q is false, the statement is false. Therefore, if you look at that chart or the truth values, you can see that they are the same. But, I mean, do you really feel it? It is a different thing. Okay, so let's prove it quickly. However, this is a very important one because you don't have any implication sign here. Proof, very important one, proof. Okay, suppose, which one you want to suppose? This one or that one? Let's suppose what did I done? I have written suppose P plus Q is true. Suppose P plus Q is true. I want to prove not P or Q is true. How do I come to the other side?
can we do one case at a time? Assume P is true and Q is
Okay, clearly.
clear.
That's a good one, good suggestion you brought. P is true, O is false. That's what you mean, no? Okay, case 1 then.
Assume that P is true.
Assume that P is true.
Then Q is true.
Then Q is true.
Uh, can we just go to P implies Q?
I'm sorry, I didn't understand.
I mean, can we straight go into the P implies Q by this?
No, we want to prove this one. We have assumed suppose P is
sorry,
plus Q.
sorry. It's true. It's true. Since Q is true, P, not P or Q is true.
So not P or Q is true. Okay, case 2. Assume that
Assume that.
P is false.
Yeah.
No?
Yeah. Is false.
Thus?
Thus, not P is true.
So,
So, not P or Q is true.
hence in either case, not P or Q is true. So we have assumed this one and have proved this one without writing much. Now, first you say, now suppose, no?
Suppose not P or Q is true.
Not P or Q is true. Okay?
Clearly, not P is true or Q is true.
That's at least one of
This one not P, Q.
not P, Q is true. Again case 1, case 2. So here since I have 1 and 2, I will say here case A.
Assume that not P is true.
So P is false, right?
Yeah.
So P plus Q is true, right?
Yeah.
Case B. Now assume that.
Assume that Q is true.
So P plus Q is true. Hence in either case, P plus Q is true. So we have, I'm not writing the last statement, but I should have written that also because your last statements are wrong in your homework.
Okay.
But anyway, I want to finish logic part today. I want to start, then what did I say? 10.2.5 theorem again is an important one. I guess. Let P and Q be statements. Anyway, you brought a good idea. You said take the negation of both sides. That is one way of proving. That is, however, when you know things. At the very beginning, we don't know much, no? So what we do is we assume that side, prove this side, we assume this side, prove this side. Or else we assume this is false, prove this is false. Now assume this is false, then prove this is false. Another way, assume this side is true, prove this side is true. Assume this side is false, prove this side is false. Many ways of proving. And take the negation of both sides if they are the same, equivalent. So there are many ways. We have to know all that. When you are going to do analysis problems, how you are going to tackle depends on how much logic you know, equivalent forms, easy ones. Okay, so let P and Q be statements, then the statement not P implies Q is logically equivalent to the statement P and not Q. That is a very important one. Very, very important. We have to know the negation of all the statements, negation of negation, then negation of and, negation of O, negation of P implies Q, negation of P if and only if Q. We have to know all of them right away. So, shall we prove this one also? Or you don't want me to? What do you? Actually, you are proving, not me.
I think
Eh?
I think I can.
You can. You also can. No need to prove this one. Okay. So let's jump there. This is 10.3.1 again, I say. However, this must be in your blood now. Negation of P implies Q is P and not Q. It must be. Not that you can prove it, but that it is with you. 10.3.1, I am saying P if and only if is logically equivalent to P implies Q and Q implies P. No, that's why it is we call biconditional. You can prove it, no? Yeah, no problem. And then 10.3.5 is again important one. Let P and Q be statements. Not P and Q is logically equivalent to each of the following statements. First one is P and not Q, or Q and not P. Can you prove it? I guess the book has chosen truth tables. I don't encourage you to choose, prove anything by a truth table. It's like, suppose now you are looking for a girlfriend, then there is a machine. When you click, press the button, it likes, oh, the machine says you are like. It's not a good way, because when you prove using truth tables, you don't know how the proof went. It comes from the truth table. So as a result, that's not a good one. However, you can prove this, no? Negation of them. Then page 67, exercise 02. Okay, let's do that some. Let us do it. Let us do it. I wanted to actually bring a different exercise for this one. I could not. Somehow I could not bring. Let me, before I write the thing on the board, this paragraph on the previous page. Ooh. That's an important one. I am saying, I will read the activity problem also. Observe that P and Q is true only on one occasion. No? Both P, Q must be true in order for P and Q to be true. P or Q is true only in 3 occasions. Right? P if and only if Q is true only on 2 occasions. Using this show that no 2 of P and Q, P or Q, P implies Q are equivalent. That is one way of saying it's not a good way, but one way of saying, sometimes when people, if you can get the answer even by a Kodivina, Anavina, some Yakshadisi, if it comes, it's good, but that's not the way to do maths. Further observe that P plus Q is false only when P is true and Q is false. P or Q is false only when P, Q are false. Hence show that no two of P and Q, P or Q, P, if and only if Q, P implies Q are equivalent. Their meanings are not the same. I mean, that's kind of discrete mathematics argument here. This is not a really good way. To proceed further, now from here, I guess in the book, this is the end of introducing these quantifiers. Not the quantifiers, connectives. Connectives, logical connectives, not and or. Not and or implies an if and only if. To proceed further, you need to understand and feel the differences among the logical meanings of the logical connectives. And O implies an if and only if. I mean, if you want to continue, you have to see these meanings are very different. That's what I am saying. This task cannot be achieved by memorizing the definitions. Just because if you memorize the definition, it won't go to your heart. Besides, this cannot be achieved by showing. They are not logically equivalent. Just because of you can show that they are not logically equivalent, I mean, you haven't achieved it. Logical. If P and Q are still, you will get the feeling through actual exercises, most probably. You cannot learn to swim just by reading books on swimming without jumping to water. You need to keep in mind the saying, if you want to go to heaven, you must die. When I teach in USA, very first time, this is a question I ask from the students. If you want to go to heaven, what you must do? American students say, you should go to church. Muslim guys say, you should go to mosque. Indian guys say, you should go to Covid. Once in a blue moon, there are some Buddhist, once in a way, some Chinese or Korean student, Buddhist, you should go to temple. Then I asked them, haven't you been to temple, church, mosque, etc.? Yes, but are you in heaven? No. So I say, if you want to go to heaven by going to temples, churches, mosques, Kovils, you will never go to heaven. If you want to go to heaven, you must die. How can you go? Similarly, if you want to learn maths, at the beginning, now to you it's very important. Because when you write, not good. What I see from you is that you understand. However, now even for this, sometimes you want to jump. You cannot do it that way. Okay, so I'm going to discuss, you want to do computer sets. These are exercises on page 67. When you go home, when you find time, now this week we are doing problems, this week and next week, you have time. So I would like you to do question 1, 2, 3, 4, all of them.
In which page?
Page 67. Page 67 and 68 both. So I am going to discuss anyway question number 2. So you have 1, 3 and 4. They are good exercises. Roman 1 is set of all x belongs to R such that x greater than 3 so x square greater than 9. Roman 2 set of all x belongs to R such that x greater than 3. Now first one is n by the way. And x square greater than 9. Third one, set of all x belongs to R such that if x greater than 3, then x squared greater than 9. Fourth one, set of all x belongs to R such that x greater than 3 if and only if x squared greater than 9. The reason I wanted to, I said that construct it. Did I discuss this kind of thing at the very beginning when I was
I think you gave it as a homework.
some problem?
We didn't discuss it, but we did it as homework.
So the thing I wanted was, I remember discussing. Anyway, no need. Now you have another 3 questions now. So we want to compute x greater than 3 and x squared greater than 9. What is that set? Because the reason what I want, first one is and, then one is or, next one is if then, the last one is if and only if. If we are getting different sets, we don't have to always, then it says that their meanings are different, no? With that hope, I guess you cannot do question number 4, you cannot do, you don't know about differentiation. So you can try 1 and 3, that's enough. Not 4, not 4. Okay, what is this set? Set of all x belongs to R such that x greater than 3 and x squared greater than 9. When you are doing a problem like this, best thing is to draw first x greater than 3 set. You have here 3, somewhere here 2, 1, 0. X greater than 3 is this set. Right? This is x greater than 3. Then x squared greater than 9. This is x greater than 3 set. Now I want to draw x squared greater than 9 set. What is it?
X greater than 3.
Okay.
And x is less than minus 3.
X is greater than minus 3.
Less than.
Okay. Now using this, we can answer this thing. X squared greater than 3 and x squared greater than 9. What is the answer?
X greater than 3.
X greater than 3. That is 3 to infinity. X greater than 3 or x squared greater than 9?
X greater than 3 and
O x squared greater than 9.
X greater than 3 union x less than minus 3.
You are saying minus infinity to minus 3, union 3 to infinity.
Yeah.
Right? If x greater than 3, then x squared greater than 9.
It is the same as the first one.
First one?
I mean x greater than 3.
What do you say? He says the first one.
The second.
Second one? He says the second. Now
Now
I have-
X is any real number?
X is any real number. This is any real number. He says it is R.
I'm thinking about the
Yeah?
negation. I'm thinking about the negation and
Okay, let me see your answer. No, there is one answer saying it is R. Let's see whether it is right or wrong.
there is none.
Hmm?
There is none.
Empty set.
Yeah.
No, that's not true. Why do you say it is empty set?
Why? Because if that statement is false, x greater than 3 and x squared is less than 9.
That's not equal to 9.
Yeah. Then that one is empty. This is true. This R.
R is true.
Yeah.
How do you get the R?
I mean, if the negation of it is empty,
You studied just before a while. P implies Q is logically equivalent to not P or Q. Right? If you take not P, x less than or equal to 3. From here, including 3 to the Soviet Union. Not P. Q is x squared greater than 9, all the way to heaven. So it is R. This is the way you decide. Then the last one, x greater than 3, if and only if x squared greater than 9.
x greater than 3.
X greater than 3. How about it?
X greater than or equal to minus 3.
X greater than or equal to minus 3, that is? That cannot be true. So you get 0, 0 greater than 3, 0 greater than 9, both are false. So he says everything minus 3 to heaven. That's what you are saying, no? Including minus 3. That's what he is saying. Is he right? Go. Now, if x greater than 3, then x squared greater than 9 is R. So the last one is if and only if Q is logically equivalent to P implies Q and Q implies P, no? P implies Q set, we have R. Now we need the Q implies P set. No? If x greater than 3, then x squared greater than 9 is R. So this one is R. R intersection anything is the anything. Now then we want the sentence if x squared greater than 9, then x greater than 3. What is this set? This is x squared less than or equal to 9 or x greater than 3. Right? Because I am going to use P if and only if Q is logically equivalent to P implies Q and Q implies P. This is correct, no? So this one we have got R. The other thing now we want if x squared greater than 9, then x greater than 3. So not P or Q, x squared less than or equal to 9 or x greater than 3. This is means x less than or equal to 3 or greater than or equal to minus 3 or x greater than 3. Therefore, all the way to, even though here it is 3 doesn't include here 3 includes, so all the way from minus 3 to infinity. You got it? Minus 3 to infinity. Now can you see? All are different answers. So that means and oh, then if and only if, whether you understand the logic, this and that. Now this one says they are different. They are different. You should be able to do this sort of questions to make sure that you understand.